attention to the distribution of the galaxies, just as people in the past had examined the distribution of stars. Now, stars don't fill the sky uniformly, and galaxies as well are not splashed uniformly across the entire sky. There's a zone of avoidance that runs roughly along the Milky Way itself, where no galaxies are seen. And Hubble correctly perceived that this wasn't real, but just an illusion caused by obscuration in our own galaxy. Well, on the large scale, then, galaxies do what the stars do not. They distribute themselves more or less equally in every direction.
But on the small scale, Hubble found something equally remarkable, that galaxies themselves tend to be found in groups, even though these 1,200-odd regions he surveyed were intentionally chosen to avoid known clusters. Even so, the statistics showed Hubble that there is a strong tendency for galaxies to group into clusters. And he speculated that possibly all galaxies belong in clusters. Well, it turns out that our own galaxy is no exception. We belong to a system of about 24 galaxies, strewn over about 3 million light years of space, which is to say light takes something like 3 million years to cross this system to which our galaxy and 24 or so others belong. We rather affectionately call it our local group. The local group contains the brightest galaxy in the sky that you can see from the northern hemisphere, the Andromeda galaxy. It contains our own, a number of other galaxies, most of them rather dwarfish, and some still being discovered from time to time. But the local group itself would never be noticed if it were, very far away, say 10, 15, 20 million light years. It would begin to fade into the background of galaxies. So if one wants to survey the distribution of galaxies at great depths in space, it's necessary to look at things that are much richer aggregates. Now, the nearest fairly rich aggregate of galaxies is that one in the constellation Virgo, where even the earlier observers noticed a concentration. The problem is that even something like the Virgo cluster would be lost if it were really as far away as the typical objects that we can now see with our large telescopes. But fortunately, there exist extremely rich clusters of galaxies, the kinds of clusters that I call the great clusters. The great clusters of galaxies contain not just a few dozen or even a few hundred galaxies like the local group or the Virgo cluster, but literally thousands. And they usually show marked symmetry with a great concentration of galaxies toward the middle and spherical symmetry. They stand out like sore thumbs, and you can see them to great depths in space. Unfortunately, there are no great clusters of galaxies that are very nearby. And to really survey the great depths of space by using the great clusters, we have to search for them. I was very fortunate, I think, to be an observer on the Palomar Sky Survey, done just after World War II with the Big Schmidt telescope at Palomar. And here's a typical photographic plate taken with a Schmidt telescope, looking far away from the Milky Way. We don't see much on the plate, a few near foreground stars belonging to our own galaxy. But if we survey this plate with a microscope or even a hand magnifier, you can see more images of faint, distant galaxies than you can of foreground stars. And indeed, by systematically surveying a photograph of this sort, you can pick up literally thousands of great clusters of galaxies extending out to distances of billions of light years from the sun.
A more difficult thing to determine is actually how far away those stars are. And with modern astronomical techniques and automation of running the telescopes with some computer online analysis, a rather effective, rapid determination of the actual distance or an estimate of the distance to the star or distant galaxy you're looking at has been developed. And so a large-scale survey of the sky in terms of 3 dimensions, both where they are on the 2-dimensional sky that we see and the 3rd dimension, the depth in the sky, has taken place in the last few years. And when this data was put together and compiled, the surprising discovery was that these stars, while they look like they're spread evenly, roughly speaking, on the sky, in fact, are not spread evenly in the three-dimensional space, but form voids and clusters, sort of a stringy, cheesy or spaghetti-like arrangement of superclusters of galaxies, where there's sort of a string of superclusters and then some space between it and another string, sort of like I said, cheesy, sort of when you're pulling hot cheese. There are long strands and spaces between them. Question is to try and think back, what does that mean of how it was packed together initially when it exploded? What was going on right at the beginning to give rise to this pattern that we now see? So this information on the distribution of galaxies and galactic clusters in space, and in fact this surprise that they're not uniformly distributed, but in fact have this kind of stringy structure, is some kind of clue which it behooves us to interpret about what was going on at a very early stage.
We can ask ourselves questions now about how this whole universe started, and how is it changing, and how will it end? And galaxies will help us answer those questions, these questions which are really at the heart of modern cosmology. Well, galaxies also tell us that the universe is changing, it's expanding, and this was discovered by Edwin Hubble, who used the Doppler shifts that V.M. Slipher of the Lowell Observatory had measured on spectrograms of galaxies. Hubble and his colleague Milton Humason obtained more of these spectrograms for galaxies. They combined their new information with Slipher's, and they found something very unique and interesting. The galaxies, for the most part, all had red shifts. Now, when we look at stars, this is not the case. Some of the stars seem to be coming toward us and have blue shifts in their spectra. Some seem to be going away and have red shifts. But almost all of the galaxies have red shifts, carrying them further away from us. Well, Hubble realized that all of the galaxies were expanding away from each other, and in fact, it was the whole universe that was expanding.
The very first observations, which eventually led to the discovery that the universe is expanding, were made here at Lowell Observatory in Flagstaff, Arizona. Here, one of Percival Lowell's associates, V.M. Slipher, began studying the spectra of distant white nebula over a decade before Edwin Hubble revealed that these white nebula were in fact other galaxies beyond our own Milky Way.
The first object for which Slipher obtained a spectrum was the nearby Andromeda Nebula. Slipher found that the spectral lines were shifted, indicating a motion of that object in our line of sight with a speed far greater than that of any other object ever seen. Well, when Lowell heard of these results from Slipher, he said, "It looks as if you've made a great discovery. Try some other spiral nebulae for confirmation." Well, over the next 20 years, Slipher observed many of the nebulae, and he found that all but a tiny handful are moving away from us, and at tremendous speeds, one of them at nearly 2,000 kilometers per second. Now, most of these observations have been made before Hubble showed that the nebulae are really galaxies, great systems of stars far beyond the stars of our own Milky Way. So Slipher had no way of knowing how far away these systems actually are. Nevertheless, his work provided the first step toward our modern understanding of the expanding universe.
Most of the galaxies appear to be moving away from us. Because the spectral lines are shifted toward the red end of the galaxy spectra as if they were receding, the visible universe seems to be expanding. According to one theory, a gigantic explosion occurred when the matter forming the universe had gathered into one cosmic mass billions of years ago. The galaxies, which formed from the exploded material, have continued traveling outward, farther and farther apart from each other, with the galaxies farthest away moving out the fastest. The rate at which the universe is expanding is defined by the Hubble constant, a number which indicates how quickly a galaxy at any given distance is moving away from us. But if we know the rate of expansion, we can calculate backwards to determine how long ago the galaxies in the universe were all together. That is, how long ago the universe began to expand. present value for the Hubble constant places the age of the universe at just under 20 billion years, which is safely older than the oldest stars we can find.
What Hubble, Thomason, and Sliver discovered is interesting and amazing. They found that the more distant galaxies have larger redshifts than the nearer galaxies. Now, the most common explanation for a redshift is motion. Motion, in this case, of the galaxy away from us here on the Earth. That motion causes the Doppler effect. And what this means, then, is that the farther away a galaxy is, the redder its light is, and the redder its light is, the larger its redshift. And the larger its redshift, the faster it's moving away. So the distant galaxies are going away from us at the fastest speeds. And in fact, all of the galaxies are moving away, and their speeds are directly proportional to their distances. Well, how do we explain all this? The simplest explanation is just that the universe overall is expanding. It's just getting bigger. And it's expanding uniformly, without twisting, without changing shape. All of the galaxies are getting farther away from all of the other galaxies. And from any particular galaxy, the Milky Way galaxy in which we reside, for example, it looks as though everything else is going away from us. Well, there's no reason for us to conclude that the rest of the universe doesn't like us. The rest of the universe sees exactly the same picture. Everything in the universe is moving away from everything else. Well, it's a short jump from the idea that the universe is expanding to the proposition that all this expansion began after a brief moment billions of years ago when the universe, the whole universe, was much smaller and much more condensed. Following an intense flare of light and heat, that expansion began, and as it did, the universe started growing larger and cooler and thinner and continued to the present state in which we find it today. Well, this picture, this idea of the expanding universe and its starting at this point is the so-called Big Bang theory of the universe. And of course, it describes a universe that is evolving. As the universe grows, it changes. And so the universe that we see today is different from the universe of billions of years ago. And of course, the universe of billions of years in the future is going to be different from the universe that we see now. Well, these universes that we talk about so glibly, of course, are really just interpretations of what we see in the galaxies and the light they send us. The Big Bang and the expanding universe itself are just interpretations of the data that Hubble collected. It's the most favored interpretation, of course, today, but still it's just an interpretation. And there was a problem with it when Hubble first proposed it, because his observations showed that the rate of expansion of the universe was really too fast. All of the galaxies were moving away from all of the others much too quickly. That rate of expansion actually implied an age of the universe that was too young, younger than some of the very objects in the universe. Well, this made no sense at all. And so, of course, it prompted some researchers to seek alternative explanations. And shortly after World War II, a competing theory for the expanding universe emerged, the so-called steady-state theory of the universe.
A steady-state universe was at one time a very attractive alternative to a Big Bang universe because the age of the universe that we deduce from the expansion of these galaxies has changed. Our estimate of this age has changed by a factor of 10 since Hubble first tried to measure it. And at the time he tried to measure it, the age came out much too short for what we knew to be the age of the solar system by dating the radioactive material in the Earth's crust and so on. And it was too short by a large factor. And so it seemed that you couldn't that in some way the universe must be older than it seemed from its expansion, and it turns out that the general relativistic equations, if you put a small extra term in those, then there's an alternate solution possible, which says that the universe has existed the same in time as well as in space. And this was the basis for the idea of a steady-state universe.
In 1948, Fred Hoyle developed his steady-state model of the universe, incorporating the original research of Hermann Bondi and Thomas Gold. The steady-state theory is based upon the perfect cosmological principle. Not only does the universe appear to be the same to all observers, but it looks the same at all times. The steady-state model also depends upon a process of continuous creation. There is no singularity or primordial atom, no distinct beginning, and no end. The universe has always been expanding, is expanding, and will continue to expand. The galaxies are created, live out their lifetimes, and disappear. However, the average density of matter in the universe always remains constant, rather than thinning out with the expansion, because it's assumed that new matter in the form of hydrogen is continuously being created and giving birth to new galaxies. Also, because new galaxies are forever being formed to keep pace with the expansion, the average separation in distance between them remains virtually unchanged as time passes. So, while the evolving, or Big Bang cosmology, contends that the matter in the universe is in fact thinning out, the steady-state theory contends that the density of matter is unchanging, and that dying galaxies are perpetually being replaced by new galaxies, formed from an infinite source of new hydrogen.
Well, from the point of view of theory, either idea could be correct, the Big Bang or the steady state. But here's where science really comes in, because we compare our observations to what the theory predicts, and we can tell that the steady state in its original form is not correct. The observational evidence discounts it. We see evolution in the universe, and we shouldn't see that in a steady-state universe. According to the steady-state universe theory, galaxies of different ages should be around us, young ones and old ones and some in the middle. But it looks to us like almost all of the galaxies are really of the same age, were formed at more or less the same time. And if we look far out into space, we're also looking very far back into time. And far back in time, things look different than they do now. For one thing, we see a higher concentration of radio sources in the past. And the quasars, too, seem to have been more populous in the younger days of the universe. But the real clincher came in 1965 with the accidental discovery of the remnants of the radiation left over from the primordial fireball, the Big Bang itself.
Now the question is, what happened to all of that radiation that was floating about in there? The first person to consider the question was George Gamow, the American physicist in the late 1940s. He predicted that that radiation should still be there, still floating around throughout the universe, all around us, because of course we're still now, as we were then, inside the universe. So Gamow predicted that we should be bathed from all directions with microwave radio radiation, the leftover glowing embers, as it were, of the fireball at the start of the expansion of the universe. Not many people took Gamow's prediction very seriously at the time because there was no easy way to observe that radiation. But in the mid-1960s, things changed.
And this is odd because it goes back to the Bell telephone labs again, where radio astronomy got its start. But this time it's the middle of the 1960s, and instead of Jansky, the names are Penzias and Wilson. Penzias and Wilson had a problem of attempting with a very accurate sugar scoop-shaped radio telescope to make absolute measurements of sources in the sky. Penzias and Wilson wanted to measure the absolute strength of the signal, and to do that, they had to know everything about their equipment and where all the radiation that they saw on their detectors, where it all arose from. And they kept eliminating things and improving their equipment and eliminating all the extraneous signals that worked their way into your system, except they were always left with about 3 degrees left over. There was a signal corresponding to a 3-degree system. It wouldn't go away no matter what they did to their equipment. It wouldn't go away no matter where they looked in the sky. It came in with the same intensity and the same level of strength all over the sky. It was persistent. At the same time, just down the road at Princeton University, a team of scientists led by Dickey was working up the idea of what happened if the universe... that was in a small volume. It all started from that, 15 or 20 million years ago, exploded outward. That was very hot. That little ball, just minutes or seconds even after the explosion, was extremely hot. That heat and that energy never escaped the universe. I mean, it's still there, but as the universe grew bigger, it cooled and cooled and cooled, till today its temperature is 3 degrees. And this discovery of the cosmic radiation or the background radiation or the primeval fireball is probably the strongest single evidence that there is saying the universe began from a Big Bang origin.
The discovery of the cosmic microwave radiation and other evidence that things in the universe are evolving or changing disproved the steady-state theory a couple of decades ago. But disproving one theory doesn't prove another. So disproving the steady-state theory doesn't really prove the truth of the Big Bang theory of the expanding universe. Still, the Big Bang idea is the favored explanation today, and it's favored for 2 reasons. One, the Big Bang theory of the universe is consistent with all of the observations that we have of the universe around us. And 2, it's the simplest explanation of what we see around us. Now that's what's important, the simplicity. When we have 2 competing theories, we choose the one that is simpler. We choose the one that involves the fewer assumptions, and so the one that, in a way, is easier and cleaner to deal with. It's always possible, of course, to think of a more complicated way of explaining the things that we see around us. For example, we could imagine that all of the electrons in the universe get heavier as they age. Now, this would mean that in the past, electrons were lighter. And we also know that lighter electrons would give off redder light. So when we look through our telescopes out into space, and then we're, of course, also looking farther back in time, we could be looking at lighter and lighter electrons the farther and farther away we look. And this pattern of younger and younger electrons at greater and greater distances giving us redder and redder light will give us a law of redshifts, a pattern of the overall appearance of the universe that wouldn't even require us to have an idea of an expanding universe and a Big Bang. Well, in fact, this is exactly the kind of thing that was going on in the theory put forward by...
It was persistent. At the same time, just down the road at Princeton University, a team of scientists led by Dickey was working up the idea of what happened if the universe... that was in a small volume. It all started from that, 15 or 20 million years ago, exploded outward. That was very hot. That little ball, just minutes or seconds even after the explosion, was extremely hot. That heat and that energy never escaped the universe. I mean, it's still there, but as the universe grew bigger, it cooled and cooled and cooled, till today its temperature is 3 degrees. And this discovery of the cosmic radiation or the background radiation or the primeval fireball is probably the strongest single evidence that there is saying the universe began from a Big Bang origin.
The discovery of the cosmic microwave radiation and other evidence that things in the universe are evolving or changing disproved the steady-state theory a couple of decades ago. But disproving one theory doesn't prove another. So disproving the steady-state theory doesn't really prove the truth of the Big Bang theory of the expanding universe. Still, the Big Bang idea is the favored explanation today, and it's favored for two reasons. One, the Big Bang theory of the universe is consistent with all of the observations that we have of the universe around us. And two, it's the simplest explanation of what we see around us. Now that's what's important, the simplicity. When we have two competing theories, we choose the one that is simpler. We choose the one that involves the fewer assumptions, and so the one that, in a way, is easier and cleaner to deal with. It's always possible, of course, to think of a more complicated way of explaining the things that we see around us. For example, we could imagine that all of the electrons in the universe get heavier as they age. Now, this would mean that in the past, electrons were lighter. And we also know that lighter electrons would give off redder light. So when we look through our telescopes out into space, and then we're, of course, also looking farther back in time, we could be looking at lighter and lighter electrons the farther and farther away we look. And this pattern of younger and younger electrons at greater and greater distances giving us redder and redder light will give us a law of redshifts, a pattern of the overall appearance of the universe that wouldn't even require us to have an idea of an expanding universe and a Big Bang. Well, in fact, this is exactly the kind of thing that was going on in the theory put forward by Hoyle and Narlicker. And when we have here two competing theories of the universe, we still do what we've always done. We choose the simplest of the explanations, the explanation that involves the least assumptions. So the Big Bang theory of the universe is still the simplest explanation of the universe we have, and in the half-century since it was first proposed, it still satisfies all of the observations that we've made that apply to this picture of the universe as a whole. The Big Bang universe, then, is the best explanation that we've got of what we see going on around us. Doesn't mean, of course, that it will always be that way or that the picture can't change. Well, we can think of our ancestors' old views of the universe, these notions, for example, of a cosmic mountain that's at the center of the earth, and that flat earth poised upon the backs of four elephants, those elephants standing upon a giant tortoise, and the tortoise swimming in a primordial sea. And to us, that idea is very colorful and very quaint, whereas our own ideas are very scientific. Well, it may be that our descendants 1,000 years from now will look back at us and our ideas of the Big Bang and the expanding universe and think that those ideas, too, were very quaint.
It may well be that astronomers will never find an unquestionable solution to the origin of the universe, which is understandable when we consider that the only physical evidence with which today's cosmologists can build their case are highly elusive clues to a mystery that took place billions of years ago. But for the time being, the evidence seems to be steadily growing in favor of a cosmological model which begins with the explosive expansion of the universe from a state of incredible density and which continues to fly outward at a fantastic rate from that long-forgotten moment of the Big Bang. centuries, theologians, philosophers, and astronomers have theorized, debated, and at times raged about a simple three-word phrase: in the beginning. In order to draw any reasonable conclusions about the origin of the universe, there are a number of assumptions that have to be considered. The first is the cosmological principle, which assumes that the various laws and processes of nature which we observe at work in our region of the universe are also at work everywhere else in the universe. By extending the cosmological principle one step further, we'd arrive at the perfect cosmological principle, which also assumes that two observers in different regions of the universe would see exactly the same large-scale structure. But in this case, the one step further is the assumption that the universe would appear exactly the same at all times.